We're going to do a couple of things. We're going to first convert from Celsius to Kelvin and Kelvin to Celsius. We learned how to do that in the last video, and we'll practice that today. And then at the end of the video, I want to talk about the mass of particles and their velocities. So let's start with conversions from Celsius to Kelvin and Kelvin to Celsius. Now, if you guys recall, the lowest possible temperature was determined to be negative 273 degrees Celsius. That's when molecular motion stops. The kinetic energy of atoms or molecules equals 0. Now, since that's the lowest possible temperature, it was determined that we should call that absolute 0, or on the Kelvin temperature scale, 0 Kelvin. Now, if we got 1 degree warmer than that temperature, so from negative 273 to negative 272 degrees Celsius, we would call that 1 Kelvin. And once again, this is just a review for you. Let's say we were 10 degrees warmer, and so that'd be negative 263 degrees Celsius. We would call that 10 Kelvin, and so on and so on and so on. The bottom line here, kiddos, if you remember, is if we want to go from Kelvin to Celsius, we subtract 273 from the Kelvin temperature. If we want to go from Celsius to Kelvin, we add 273 to the Celsius temperature. So pretty straightforward. So let's practice a few of those. Let's say I'm at 0 Celsius. 0 Celsius is lots and lots warmer than the lowest possible temperature. Isn't it 273 degrees warmer than the lowest possible temperature? So that would be 273 Kelvin. We added 273 to the Celsius temperature. Now, why don't you try the next 3 on your own? So you can pause the video, try B, C, and D on your own, and then press play, and we'll see how you did. All right, welcome back. So on letter B, we have 25 Celsius. If you add 273 to that, don't you get 298 Kelvin? So that would be 25 Celsius in Kelvin. What about negative 55? Negative 55 is pretty doggone cold, but on the absolute temperature scale, it's going to be a number that's bigger than 0. So when we take negative 55 and we add 273 to that, we get 218 Kelvin. Now that might seem warm to you, but remember, that just simply means it's 218 degrees above the lowest possible temperature. Okay, now, letter D, 223 degrees Celsius. So 223 plus 273 gives us 496 Kelvin. Did you get those right? All right, let's go on and let's work from Kelvin to Celsius. So if I'm at 15 Kelvin, that's really, really cold. That's only 15 degrees above the lowest possible temperature, which was negative 273. So 15 degrees higher than that would be negative 258 degrees Celsius. Once again, to go from Kelvin to Celsius, we're going to subtract 273. So why don't you pause the video again and try letters F, G, and H, and come back and we'll see how you did. All right, welcome back. So 298 Kelvin, if we subtract 273 from that, that gives us 25 degrees Celsius. 337, so if we take 337 and subtract 273 from that, we get 64 degrees Celsius. And finally, 147, if we subtract 273 from that, we get negative 126. So make sure, kiddos, that you can convert from Celsius to Kelvin and Kelvin to Celsius. Pretty straightforward. We'll make that part of your next quiz. Okay? All right, the last thing I want to talk about today will be the mass and the speed or velocity of particles. So let's take a silly example. Let's take a monster truck, which weighs a few tons, and compare it to a toy truck. Is it possible for these trucks to exert the same amount of force? Can they have the same amount of kinetic energy? Now, most of you, your knee-jerk reaction would say, no, Hummer, that's ridiculous. This monster truck would have lots more kinetic energy than the toy truck. And I'd ask you, well, why? And you'd say, because it's more massive. right? Isn't it bigger by many times than the toy truck? You can say the toy truck is less massive. It has a smaller mass. But kinetic energy, kiddos, is more than just the mass of an object. In fact, you're going to learn, or maybe you already have in your physics class, that kinetic energy is equal to 1/2 the mass times the velocity squared. So it's more than just the mass of the particle, or in this case, the trucks. It also has to do with their velocity. So if I ask you, can these trucks exert the same amount of force, you'd have to say, well, there's more to it than mass, Mr. Hummer. We have to consider the velocity of the trucks. And you know what? I think they can have the same amount of kinetic energy, or the same force, if the more massive truck moves slow, much slower. Or you could say the less massive truck would have to move fast. You guys agree with that? So it is possible for this truck right here to have the same kinetic energy as this truck here if that tiny one's moving really, really fast and the big one's moving really, really slow. Well, the same thing is true at the atomic or molecular level. Particles with a bigger molecular weight have the same energy as particles with a small molecular weight. And you say to yourselves, well, how can that be? Well, the small ones must be moving, that's right, faster. Or you could have said the big ones must be moving slower. So it turns out the average kinetic energy of all gas molecules are the same at a particular temperature. However, of course, you know now the velocities are different because they have a different molecular weight. So the kinetic energies are the same, but their velocities are different. So molecules with a big molecular weight, so let's just say heavy molecules, would have a slower velocity than light molecules. They would have a faster velocity. To make up for their size, they have to move faster. Just like the toy truck has to move faster than that big, massive truck to make up for the small truck size. So let's give an example. In fact, I do a demonstration for this that you'll see on a demonstration video. Let's say I had light molecules like hydrogen gas. They have what's called an atomic mass of 2, and it's called atomic mass unit. We'll learn about that in a later part of this trimester. Compared to sulfur hexafluoride. Now, sulfur hexafluoride is quite a bit bigger. They weigh, on the atomic mass unit scale, around 150 atomic mass units. So sulfur hexafluoride molecules are 75 times almost bigger than hydrogen molecules. So, which one would move faster? If you said hydrogen would move faster, you would be correct, because they have a much smaller weight, or molecular weight, atomic mass in this case, than the molecular weight of sulfur hexafluoride. If I asked you which of those two had the same energy, hopefully you would say the kinetic energy of H2 will equal the kinetic energy of sulfur hexafluoride. Their energies are the same, and for their energies to be the same, the smaller one has to move faster. Okay? I think you'll enjoy the demonstration I do for you. I actually breathe in some hydrogen gas and speak, so it has the same effect as helium, and then I breathe in some sulfur hexafluoride, and I won't tell you what happens with that. Hopefully you'll be surprised. Anyway, we'll talk to you soon, kiddos. Have a great day. Bye-bye.